Hello, ladies and gentlemen, welcome back. It's been a while, obviously. So long, in fact, that we're now on to our next unit. Physics. Hopefully you guys have had some good luck finishing the ecology unit on your own. But for this particular unit, I figured that you guys would maybe need a little bit more of the direct touch. So, flipping over the page here right away, we can take a look and see that in this course, we're going to be studying many things. And the first question that comes to mind is, what in the world is physics? So, normally I would get you guys to do an activity, a brainstorming one, much like you guys did the first day of class for chemistry. You could certainly attempt that now. Pause the video, give it a shot, try to think of what you think physics is. And much like you saw when we did chemistry, you'll probably be surprised at how much you actually know. Because usually people will start putting things together and they'll be like, well, it involves moving, it involves thinking about things, it involves like energy, it involves Newton's laws. These ideas will come out because at the end of the day, you guys do know a fair amount of stuff. You just don't know that you know it yet. So what is physics? What we can put in that blank is going to be the study of motion. And that's what it comes down to. You're going to be studying movement. Chemistry, we said, was the study of matter. And ecology, we said, was the study of living things and systems. Well, physics is the study of motion. Now, as you can also see on this page here, you have multiple ways to represent physics. Words, yes, obviously, there's lots of words in this book, but we also use pictures, we use formulas, we use symbols, we use numbers. We use loads and loads of different things, all to give us a sense of what's going on. Now, trying to figure all that out, trying to put all this together, it takes a little bit of practice. You'll see at the bottom of your page some examples of pictures, graphs, symbols, math. Over time, you'll get better at all of them with practice. That's the key. And there'll be lots of practice in the book. If you guys flip over the page, we're going to do a bit of an introduction of physics. So the first thing we got to do is fill in some blanks. Okay, so here we go. Our first blank is going to just be motion. Motion is the movement from one place to another, from point A to point B. How would you draw that? What would you do? Right? Like I just told you a sentence, but what does it mean? There's a box there. Take a moment and think about it. Again, pause the video, ponder. Motion. How would I draw point A to point B? Probably most of you have done something kind of like this. Here's point A, here's point B that I'm covering up, and then they draw an arrow. That's point A to point B. An arrow pointing to where you go. This is our first example of drawing it to represent the whole thing pictorially with a picture. Okay, so that's done. Next blank. Blank is the science of describing the motion of an object using words, diagrams, numbers, and graphs and equations. We will look at the different words used to describe motion in a second. Blank. This is a big fancy word. The word is kinematics. It comes from the Greek. It means motion, or at least the first part does. Those of you who might be interested in studying at university, maybe you'll take kinesthesiology. See, it's got that same starting word. Kinesthesiology is the study of movement. It's the study of human movement specifically, so you like sports. Kinematics is the study of movement of stuff. So, cars, balls, planets, bullets, any number of things. So now, you got another box below. And it says in the box, I want you guys to write out any words or phrases that you might use to describe motion. Go ahead. Give it a try. It's anything, any word that comes to mind or phrase that might mean motion. Some get you started. Maybe something like quick, fast, or slow. That describes motion, right? It's something slow that tells you something. Movement. What are some others? Zip. Something zips along, moves pretty quick. One of those weird things about English, one of many weird things about English, but in this case, a good thing, is that words that talk about fast actually are kind of fast to say, right? Zip, fast, quick. They're all speedy. Oh, there's another word, speedy. Now, it mentions down here, you may have included the word fast in your box. What does fast actually mean? Like, if I point to something and say that's fast, most of you will be like, yeah. Or maybe you'll be like, what is Mr. C doing? Why is he pointing at something? What's happening? I wasn't paying attention. Either way, we'd have a conversation. But when it comes to fast, what is the actual definition? If you had to describe it to somebody, if you had to tell somebody that's fast, and they're like, I don't understand what fast means, could you explain? First of all, you'd probably look at them and be like, what? But then afterwards, you'd be like, okay. This is a tricky one. It's usually difficult to describe things that we kind of already know. So, what is fast? What are some features of something that's fast? Well, if it's fast, it's going to cover ground, right? So you're going to cover ground. Right? So for example, I go from here to there. I covered some ground. Now, would that be considered fast that I just did? Maybe not, but that might be considered fast, or at least faster. So what's the other component? Well, the other component is time. If you take a long time to get from here to there, it's not very fast. If you take a short time, it's pretty quick. Lastly, it says for you to draw a picture about what fast would look like. Right? So this is asking, do you guys know how to draw? I don't. Don't worry about that. So for example here, if I go with a quick sketch of a car, this is my attempt at a car. Window, little person back there. So I guess it's more of a truck than a car, but whatever. How would I show this is going fast? I can't animate it. My drawing skills aren't that good, obviously, but I can still depict that it's fast. And usually the way that we do this is that we put speed lines. Speed lines imply motion. And there you go. That is a diagram for physics. Yeah, you don't actually have to make it nice. Generally speaking, if the picture gets too nice, that usually means the students don't know what they're doing because they're too busy drawing. Physicists will draw these kind of pictures all the time, and they use them for a lot of different things. So there you go. That's our starting point. That's our introduction. Let's flip over the page, see what else we can find. Now, we've got some terms here. We've got an unusual word. And what we're going to see is that words come up an awful lot. What do these words mean, though? And why use them? So, the way physicists work is that they tend to come up with words to describe very specific ideas. And part of learning any science, but just anything, is about learning the jargon, the language to describe it. The way I usually explain this is I ask, how many people are familiar with tools? And most people in the room go, I'm not. But a couple people will usually put their hands up. And I'll end up asking them, okay guys, so if I were to ask you to get me a Phillips screwdriver, do you know what that is? And the answer for most people is no. A couple people will know that that's the screwdriver that looks like an X when you look at it straight on. And then I ask, how many people know what a Robertson screwdriver is? And then a bunch of people, again, I don't know what that is. That's the one that looks like a square when you look at it straight on. So why do we have the names? Like, we don't need them. I could just tell you, hey, go get me that X screwdriver. Or go get me the square one. And those will work most of the time. Generally speaking, we're okay with descriptions in a lot of cases. But a single word, Phillips, Robertson, is faster and easier to use when the people in the conversation know the language. If you're on a construction site, you don't want to be sitting there going, hey, could you go get me the X screwdriver or the square screwdriver? Because they'll be like, you don't know what a screwdriver is? Come on, guy. You're supposed to be working here. That's what we see here. I don't need the names to be able to use them, but if I have the names, I can talk about them easier. And the same thing is going to happen with physics. There is terminology, there are words, and if you learn them, it makes it easier to talk about stuff. So our next word is for the next page. Scalar. It's a strange word, that's for sure. It's a physics word. And there's a couple blanks here. Scalars have only magnitude. Magnitude. What does that mean? Well, it's in brackets there. A value or a number. So magnitude is a value or a number, and it then says, and no blank. And the blank there is going to be direction. It even almost looks like a D. You see, I haven't had a lot of chance to practice writing on a whiteboard, so my writing's getting even worse. So scalars are a number with no direction. Why does that matter? Well, we'll get to that in a second. Just a second. Scalar quantities are represented in symbolic form using a lowercase letter. What does that mean? Symbolic means with a symbol. And we use a lowercase letter. Technically, we could use any symbol. You guys actually know a whole bunch of symbols, okay? So, for example, that's a symbol. It means happy most of the time. Sometimes it means sarcastically not happy, but people are complicated. That's a symbol. That counts. That works. Anything can be a symbol. Now, physicists aren't usually that happy. They're too much busy working, so they don't use symbols that are that nice. Instead, they use letters. So you can see here in your notes, and its symbols are D, V, T, and M. And then there are some blanks for what in the world those names are. What are we going to call them? Well, again, you actually kind of know what most of these symbols are, if you really think about it. The V might be throwing you off. T, though, come on, T. You know T. T is going to be time. And D, well, that's distance. Again, you know that one. V, V's tricky. V is going to be speed. And then the usual question is, okay, wait, why is V speed, not S? Like, come on. There are two answers for that. First one is that physicists like to make students suffer. Most of the time. Second reason is because seconds are in S. So you don't want to get people confused between seconds and speed. It's a bit of a difference. M. It's mass. Or as you probably talk about it every day, weight. Weight and mass are technically different in physics. They mean different things, but for everyday normal English, you can call it mass and that's fine, or you can call it weight and that'll be okay. People will know what you're talking about. And the key is that if we look back at our definition of a scalar, magnitude but no direction. No direction. Well, that makes sense, right? Time doesn't have a direction. You can't tell someone that it's like up time or down time or left time. I'll meet you in 6 right time. What does that even mean? It's just time. Time is just time. That's it. Mass, well, you don't weigh like a clockwise amount of mass. You know, oh yeah, today I put on some weight. I've put on, 16 counterclockwise kilograms. Yesterday you lost weight. You lost, 12 west kilograms. That doesn't make sense. You don't have a direction for weight. Speed and distance are the same. The police, if they pull you over, not that they ever would, of course, because you guys would never speed. But if the police were to pull you over, they won't be like, sir, do you know how fast you were going in this direction? Because they kind of think you know which way you were driving, hopefully. So they just talk about your speed. How fast were you going? How much ground were you covering? I don't really care which way you were moving, just what were you doing? Distance is just the separation between 2 points, from here to there. We already talked about that on the previous page. So there you go, scalars and a bunch of examples. And they have some examples down there. 25 meters, 100 kilometers per hour, 5 hours, 40 kilograms. Okay, so why are we talking about scalars? Magnitude, over there, magnitude, but no direction. This is a binary choice. We've talked about those before. Yes or no, up or down, left or right. What's the next binary choice? Well, if this is a number with no direction, obviously the next option is a number with a direction. There we go. And this is the next thing we're talking about. Still on the same page, and it's got another weird name. It's called a vector. So a vector has a quantity that has there's a blank there, a magnitude. Oh, look at that. It's already on the board. And that number also includes a direction. Huh. There. Pointing through a camera is proving difficult. Now, vectors are drawn a little differently when we want to do a symbol of a vector. So if we want to draw the symbol of a vector, we're going to use an arrow. That's our next blank. What do I mean by an arrow? Well, vector quantities are represented in symbolic form using a bold lowercase letter. This is mostly for computers because arrows are hard to do on computers. So bold lowercase letter or an arrow. What do we mean by an arrow above it? Take a look on your page. You can see it there. You've got some bold letters, D, V, A, and F, G. I wonder what the F, G is. And then you've got some symbols without bold. And if you look at those, you can see that you've got D, V, A, and FG with an arrow. Now I think you can agree that putting arrows on a computer would be tricky. That's why they introduced the bold thing. So if you guys had a textbook, which you don't, but if you did, or if you looked on the internet and you tried to look this stuff up, you'll probably end up seeing, instead of these arrows, you'll probably see bold letters. Probably. Now, these also have names. What are the names, though? That's a little bit trickier. A, maybe we know. Maybe. But you know what? rather than start with A at the start of the alphabet, we're going to start over here on the left. D. This one would be position. And again, why isn't it just a P? P gets used for other things in physics, so they end up with D. The other reason is because, a little bit of a hint to help you guys, displacement, position, my bad, we'll get to displacement later. Position and distance are connected. They're very similar, so they both use the same letter, but one of them has an arrow and one of them doesn't, to try and make it easier. You don't have to memorize as many things. V is a term you have probably heard. Velocity. Velocity is like speed, which is why they share the V. The difference is it's got an arrow, which means that it cares about direction. So again, with the police pulling you over, they would be more of a, less of a, you were going 180 zone, and more you were going the wrong way down the one-way street. Direction matters in that case. Also, you're in a lot of trouble. Don't do that. A, that's going to be acceleration. And acceleration is probably the term in physics that is the most abstract. It's the most disconnected from our everyday life. You see acceleration all the time. Once we start talking about it, you're like, oh, I know what that is. But it's the hardest one to really see. Position, where something is, that's there. Now it's here. You could all see that. Velocity, how fast it moves, you can tell if I pick this up and move it slowly, or pick it up really fast. Acceleration, sort of foreshadowing what's going to come later. Acceleration is if I'm speeding up or slowing down. So if I pick this up and it's going slow at first and then gets faster and faster and faster and faster and faster and faster. So that would be acceleration. But it's harder to see, so it makes it harder to do. FG, that's our last one, and to be fair, I honestly just put that one in there to talk about the nature of FG. And what we're seeing with FG is that this is the physics term for weight. Now, the way I usually explain this is that, mass and weight are separate. Now, again, in everyday conversation, we usually use the word to mean the same thing. And there's nothing wrong with that. In physics, we talk about them differently because, well, for example, if you go into space, you're weightless. You have no weight. You're not massless, though, right? Because you still exist. You still have an arm. You still have a body. But that body doesn't have any weight because there's no gravity pulling on it. I mean, most of you hopefully remember that gravity is what causes weight. So weight has a direction. Weight pulls, down. That's why things fall, obviously. But mass doesn't, which is why you can have a mass up in space. That's about it. So, the bottom of the page, you guys have got a big chart. I want you guys to try filling things in on that chart. Again, pause the video, give it a shot, see what you can do. Most of the symbols are on these two pages, and you've got some examples of units. But of course, I will show you what the answers are in a second. All right, so we got the quantity. AKA whatever we're talking about. We got ourselves a symbol. And we got ourselves some units. We're asking, is it a vector or is it a scalar? And then finally, formula. Now, a lot of these we're going to fill in, especially the formulas. We'll fill those in later. But think of this as like a little cheat sheet. You can look here, boom, it's all in one place. So we're going to fill in some of these formulas. We'll probably come back, do those later. You can, of course, look ahead. They're in your booklet, so there's nothing stopping you from doing it. All right. Our first one, time. Symbol is T. Units are going to be either seconds or hours. Now, to be fair, I use SEC and HR. Those aren't completely accurate. Seconds are usually just S by themselves, but I tend to put the EC there just to make sure there's no confusion by anybody. If you continue in science, they will use S. This is a Mr. C does it, not everyone else does it. Vector or scalar, well, we already said this guy is a scalar. Formula later. Next one is going to be distance. That's a D. Units are in meters and kilometers. And this is also a scalar. Next one is displacement. This is going to be a really weird symbol. We'll talk about this soon enough. Just write it for now. It's a triangle and then the D with the arrow. Okay, so we'll see what this means in just a second. It's also measured in meters and kilometers, though. We'll put a little marker here between them. And this one would be a vector. And we got ourselves some mass, and some weight. You'll notice there's a connection between each pair. Mass is in m's, weight is in FG's, with a little arrow on top. Both of the units here, this one's in kilograms, and the units for weight are actually kind of weird. They're in N's or newtons, named after this guy you may have heard of. He's somewhat famous. Mass, of course, is a scalar, and weight is a vector. Next, we've got speed and velocity. And that moment when you realize that you're running out of board space. Oops. Speed is V, velocity is V arrow. Will that be confusing at times? Yes. Sorry. Blame the physicists. The units are either meters per second or kilometers per hour. This is true for both of them, so I'm only going to write it once. And of course, speed is a scalar and velocity is a vector. Now we've only got one left, which is acceleration. I'm going to erase time, put it up there, so anyone who skipped ahead in the video is going to be like, what happened? Acceleration, its symbol is A with an arrow, and it's measured in meter per second squared, and it is a vector. We'll talk about that a little later on. We'll get to acceleration soon enough, but patience, patience. Okay, so there's the overview of vectors, scalars, and all those other things that we're going to be looking at. At this point, we're going to take a look in more detail about distance itself. But this introduction is probably where I will pause and then start a new video. So hopefully this is working out pretty well.